Hello everyone, welcome back. We are discussing about turbulence models, particularly the eddy viscosity class of models, where we try to basically find out all the Reynolds systems by using a single variable, which is the eddy viscosity, right. And we use the Bouguenos hypothesis, and we relate the stress with the eddy viscosity and the strain rate. Okay. So, in the last class we discussed about the K epsilon turbulence model. So, the K is the turbulence kinetic energy and epsilon is the dissipation rate, and we found that by using these two variables, by basically finding the transport equations for kinetic energy, turbulence kinetic energy and the dissipation rate, we can find out the eddy viscosity, which was, let us say, if I can write it here. So, nu T was like equal to C mu K square by epsilon, right. So, K had the unit of meter per second. So, this was meter per second square and this is meter square per second cube, and cu mu is a constant whose value is typically taken as 0.09, okay, and that can be basically found out from the experimental data. Okay. So, that gives you the unit, if you take the entire thing, that gives you the eddy viscosity, which is of the unit of meter square per second, kinematic eddy viscosity, right. And from this you can also, if you think in terms of nu T equal to u 0 L 0, then also the u 0 is like basically square root of k, and then L 0 will become k to the power 3 by 2 by epsilon, right. So, this is your u 0 and this is your L 0 and then some multiplying constant. Okay. And we saw that this K epsilon turbulence model does not do very good very close to the wall, right. So, we actually discussed about the low Reynolds number model also, basically had Reynolds number is the Reynolds number, and we saw that very close to the wall you need to do some special things, use some kind of damping to get the behavior right. But even with that damping, the K epsilon turbulence model is not considered to be very good very close to the wall, especially let us say you have very high curvature as you see in the turbine blades or in many different configurations. K epsilon turbulence model does not do very well. So, that led to development of another class of model called the K omega model. Okay. So, the K epsilon model, as you know, that is a family of models. You have standard K epsilon, you have RNG K epsilon, you have realizable K epsilon, and that was like I think in the from 1970s several versions have come, starting from the original work of Spalding. Okay. So, K omega also has several versions, okay, and like we have Wilcox K omega, we have Mentor's K omega, and there are many different versions in between. Wilcox himself has many versions. So, when you are using a K omega model, okay, you should basically know that which version you are using. Nowadays K omega model by itself is not used, what is used is SST K omega model. So, these two models are different, K omega, standard K omega and SST K omega, both are different. We will discuss about those models in this class, and we will also find out why the K omega model is not used, standard K omega is not used in practice in CFD simulations, right. So, let us look at this standard K omega model. Okay. So, as we know that we need two quantities to basically model this eddy viscosity or the turbulent viscosity. So, in the K epsilon we had this turbulent I mean K was the turbulence kinetic energy, which is given as half u prime square plus v prime square plus w prime square, right, and then we had the dissipation rate, okay, epsilon, which is was the turbulence dissipation rate is given here. So, unit was meter square per second cube, okay, which was something like del u I j by del x j, del u I by del x j, okay, something like that. There is a quantity. Okay, so this represents that how the dissipation is happening. Okay, so what we do in this K omega model, that instead of using a turbulence dissipation rate, we define another quantity which also basically characterizes how the dissipation is happening in the flow. Always remember that original diagram that we had, the energy cascade, that the famous Richardson's poem, that big holes have little holes and they feed on velocity, and little holes have even lesser holes which feed on viscosity. Okay. So, you have something which is basically the kinetic energy is coming in and this is going dissipated here at the smallest scale. So, you need some equation which tells you that how the kinetic energy being produced, transported, how the kinetic energy changes between the different eddies, and something which represents your dissipation. So, in the k epsilon we had this k and epsilon, two things, but now in this k omega model it is a slightly different model from k epsilon. Instead of epsilon we are going to use a quantity called omega, okay. And omega is called the specific turbulence dissipation rate, okay, and its unit is 1 by second. So, in a way it represents that at what frequency the eddies are basically getting formed and getting destroyed, okay. So, that is the measure what omega gives you, right. So, because its unit is 1 per second, so it is a kind of a frequency, okay, and it can be related to your epsilon, right, because this is also representing dissipation rate by epsilon by k. So, omega is 1 by second, okay, k is meter per second, meter square per second square, and you have epsilon is meter square per second cube, okay. So, the quantity which is epsilon by k, okay, that will become your that will be proportional to your value omega, right, because this is meter square per second cube and this is meter square per second. So, that will give you 1 by second. So, you will take this, I mean if you go, so this C mu term, okay, you can it depends on many models, okay. In many models you do not use C mu, in many models you use that. So, that also you have to be very careful, okay. But yeah, if you are using the C mu term, omega is equal to epsilon by C mu k, right. And if you go for the definition of nu t, so nu t by C mu k epsilon by epsilon earlier. So, this will become C mu and k square by, you put the value of epsilon, okay. So, that will be your omega, I am putting the value of epsilon from here, omega C mu into k, okay. So, the C mu gets cancelled out and this becomes k by omega, okay. So, now our task is to find a transport equation for omega. K equation is as we have discussed, this can be derived from the first principle, although you can basically make some of the assumptions about how certain terms which are not very important, like we saw that viscous transport of the kinetic energy or certain stresses, that you can basically omit, okay. So, there are some modeling aspect there, but it can be derived from the first principle, and omega model like the epsilon equation, omega equation also has to be basically completely modeled, okay. The equation will be completely modeled, okay. So, we need to find out the equation for k and omega. Once you find k and omega, at every time step we can take the ratio of these two and get you this nu t, okay. So, let us look at those equations. So, the k epsilon we have already here. So, this is basically p k and we know meaning of each term, okay. This I am showing for the incompressible flow, okay, and you have sigma k and sigma omega. So, earlier you had sigma epsilon here. So, okay, let me look at this picture for the compressible flow first, okay. So, we had in turbulence kinetic energy, we had this temporal term, the advection term, the diffusion term, and many terms in the diffusion we had ignored, okay. For example, the diffusion due to the pressure, okay, or the viscous effects, we have ignored that, and then we have this sources and sinks, okay. So, taking the inspiration from this equation, we will get this omega c n per omega, replace the k with omega and make sure that you have basically all the terms that you require. So, the time dependent term of omega, how the omega is getting injected in the flow, how it is getting diffused, okay, and like the way you had sources and sink in the k equation, you will have sources and sink in the epsilon equation also. So, for example, the production of kinetic energy was the source and the dissipation of the kinetic energy was the dissipation. Here it will be basically, okay, there will not be any gamma term here. So, this is the modified term for the omega equation here. So, p k omega by nu t, and there is another term for production of the dissipation, specific dissipation rate, and destruction of the dissipation rate, okay, or basically dissipation of the dissipation rate, okay. This will be omega again. Okay. So, we got the equation for the k and omega. Okay. If you look at in a simpler form, okay. So, I will come to this gamma. This is basically taken for a transitional model, because right now you can just think of it 1 by mu t. Okay. So, this is for the incompressible flow, that is why you see there is no rho here. Okay. So, I am giving equation for both compressible and incompressible flow. Okay. And this is how the equation looks like in the incompressible flow. Okay. So, what we note in this is that the coefficients that we had earlier, we had the C epsilon 1 and C epsilon 2 in your dissipation equation in the K epsilon model. Now, the terms model coefficients we have are like basically kind of beta. Okay, now the sigma w, and there is a certain difference between the epsilon equation and omega equation. It is not that if you put epsilon equal to or omega equal to epsilon by s mu k, you will get the omega equation. That is not the case. Okay. So, there are certain terms which are missing. It is just that inspired by the kinetic rate equation, we modeled a dissipation rate equation and we got some coefficients. Okay. So, these coefficients are basically different from the k epsilon model, but the beauty of this model is that it basically solves all the way to the wall without any damping function or anything. Okay. In fact, this model is very good for the wall. Okay. So, whatever damping that you need near the wall, you want to basically model the viscous sublayer or the laminar sublayer, the log layer and all those things, this model can do very well. Okay. The way the coefficients have been tuned in this particular model, that you do not require any damping function, it is in by default it is a low Reynolds number turbulence model. Okay. So, it works better very close to the wall. Okay. And it's better in, and because of that reason only, because whenever you have this adverse pressure gradient or there is a separation, right, that those things, effects of those things are seen in the boundary layer. Okay. And because this model works very well near the boundary layer, this is very good for this kind of flows. Okay. But the problem with this model is that it is very sensitive to the free stream turbulence. Okay. So, once you, when you try to do a range simulation, you specify certain values. For example, you give the turbulence intensity which is given as I. Okay. This is basically in a way you can call it that this is u prime by u. Okay. What is your fluctuation, estimated fluctuation with respect to your free stream velocity. Okay. And then sometimes you give the length scale. Okay. Sometimes you give the ratio of the eddy viscosity to the dynamic viscosity. All those kind of things you can give, right. So, one is very important, which is the turbulence intensity. Now, what problem with this particular model is that, let us say you do a simulation with a turbulence intensity, free stream turbulence intensity of around 10 power minus 5, okay, and get certain results. Now, you change it to, let us say something like 5 into 10 power minus 5, okay, and there will be drastic change in your results, okay, in terms of, let us say, prediction of separation or the skin friction and all other things. So, this model was found to be very sensitive to the free stream turbulence. Okay. So, because of this sensitivity, this model is not very good, because you know, when you do an experiment and you try to measure the turbulence, there is always some uncertainty. Okay. And if the model does not account for that kind of uncertainty and gives you very drastically different results, then the model is not good for your CFD. Okay. So, that is the reason this model is not very good, it does not work well for a wide class of flows. Okay. So, to improve this situation, we use some kind of model which is called the K omega HT model. So, what it does, so you have this K omega model. Okay. So, just let me draw a picture here. Okay. So, let us say this is your boundary layer, okay, and this is your free stream. Okay. So, you have a model which works very well here, which is K omega model, okay, and then there is a model which works very well, which is the K epsilon model, which is away from the boundary layer. Okay. So, can we basically blend this model and propose a new model which has the advantage of both of them. Okay. It is not very sensitive to the free stream turbulence, that is what the K omega epsilon is, and it solves the flow accurately very close to the wall, that is the K omega, right. So, that blending is what is called the SST k omega or k omega SST. Okay. So, SST is here stress transport and k omega is q omega. Okay. So, let us look at that model now. Okay. So, once again k omega epsilon model is very good, very close to the wall, but it is extremely sensitive to the free stream turbulence, and that is why it is not very useful, because you will always have uncertainty in your measurements, or you do not want the thing to change drastically if your turbulence intensity shifts by, let us say 5%, or I mean the intensity shifts by certain value like 5%, 10%. Okay. You want your model to be robust, and that is what you see in your SST k omega turbulence model. Okay. So, to learn about this SST k omega or k omega SST model, okay, let us review the epsilon equation in the k epsilon model. Okay, we want to compare this dissipation term in the k omega model and the k epsilon model, that is the purpose. Okay, so, this is the equation that we have for the k epsilon model for the epsilon transport equation. Okay. Now, what we do is that we take this epsilon, we know that omega is equal to epsilon by c mu k. Okay. So, why do not we just put it here, okay, and can we derive a omega equation, right. So, of course, we can do that, just replace the this epsilon by omega c mu k, okay, and try to derive an equation. Okay. So, what we will see that you will get the equation which looks like this. Okay. So, remember we are using the epsilon equation from the k epsilon model and putting epsilon equal to c mu k omega. Okay. So, this gives you an equation, of course, you have to do some manipulation there and take the help of the k equation that you already have. So, this is the equation that you are going to get. Okay. Now, this term is there in your k equation also, this is also there in k equation, this is also there in k equation, okay, this is also there in k equation, but this is the term which is not there in k equation. Okay. So, this is a kind of cross diffusion term between the turbulence kinetic energy and the specific dissipation rate. So, if you take the epsilon equation and try to derive your k equation from that, so this is the equation, omega equation from that, this is the equation that we get, and this is different from the omega equation that we use in the standard k omega, which is basically just taking the inspiration from the turbulence kinetic energy equation and using some model coefficients, right. So, this equation, I mean this term may also be responsible for this very weird behavior of the k omega model, that it is very sensitive to the free stream turbulence. So, what we want to do that we want to somehow retain this term, okay, away from the wall, right. If you retain this term away from the wall, that means you are essentially solving the k epsilon model, right, because this is nothing but the k epsilon model, okay, and make this term disappear very close to the wall, so that it is able to give the damping that you get from the k omega model. So, if you remove this term, okay, what you are getting is the standard k omega model, the k equation for the standard k omega model. Okay. So, that is how this term will become. So, this is your k equation and this is your omega equation, okay, and then you will have additional term, but remember here it was 2 rho sigma omega 2 again sigma omega is a coefficient, model coefficient omega delta. So, this is basically a term which is basically multiplies each term of delta k and delta w. Okay. So, this will be k by delta x, delta w by delta x plus delta k by delta y plus delta w by delta y and delta k by delta z, delta w by delta z. Okay. That is the term that it is represented here. Okay. So, we want to retain this term. So, instead of basically solving 3 different equations which will be expensive, you can do it, maybe you can solve k epsilon and omega 3 equations, okay, and then basically use k omega near the wall and k epsilon away from the wall, right. But instead of doing that, why not we use this k omega only equation, which is this omega equation, but use some kind of blending, so that this term goes to 0 very close to the wall and becomes 1 away from the wall, right. But the blending has to be done in such a way that there is no abrupt jump. Okay. So, that is what is done in the SST k omega model. So, you can see this term which is basically 1 minus f1 term. Okay. So, what does this 1 minus f1 term does is when f1 equal to 1, I will show this behavior of this term. Okay. This depends on the distance from the wall. Okay. So, when f1 is equal to 1, you can see that this term goes to 0, okay, and then that will become q omega. So, that means we want f1 equal to 1 very close to the wall, or 1 minus f1 to be 0, and when f1 equal to 0, the equation is k epsilon. Okay. So, one thing I am not explaining. So, I have been using this term gamma. Okay. So, for now you can take gamma equal to 1 for all this flow. Gamma is a representation of intermittency, okay, which is I will talk about it very soon, maybe today or in the next class. It is like if you have a boundary layer which is basically laminar and that becomes transitional and then become completely turbulent. Okay. So, then this value of gamma is equal to 0 here, and in the fully turbulent region this is equal to 1 and this is basically 0 and 1. Okay. So, these are fully turbulent models. So, we take gamma equal to 1, okay, by default, but this gamma term is very useful. Let us say if you want to do for the transitional flow, where the flow can be laminar in some region and turbulent in some region, in between it can be transitional, right. So, for now you can assume this gamma to be equal to 1, okay, or you can remove this term also, okay, in the SST k omega model. Okay, but what I am trying to say that we want to retain the behavior of the k omega model very close to the wall. So, that will be given by this function 1 minus f1. So, if f1 equal to 1, the equation is k omega, f1 equal to 0, equation is k epsilon, and also we can not only do blending here, but we can use this parameter f1 which is the blending parameter to get this behavior everywhere. I mean, you let us say you have C epsilon and alpha somewhere. Okay. C epsilon is the coefficient which is there in k epsilon, and alpha is the coefficient in k omega. So, you can use this kind of blending in those all the parameters that you want for the omega and for the epsilon. Okay. So, whenever f1 equal to 1, this is behavior of omega, and f1 equal to 0, it is behavior of epsilon, right, and this f1 depends on the distance from the wall. Okay. So, if you plot this f1, okay, so here I am plotting 1 minus f1. So, because I want to show how this thing works about between the k omega and k epsilon, this is more natural to understand. So, when f1 minus f1, so when f1 equal to 0, 1 minus f1 equal to 1, okay. So, that is the point which is very close to the wall. So, they say this is my wall, okay, this is my y, okay. So, this is very close to the wall. So, the value 1 minus f1 is equal to 1, okay. So, no, so if it is, if 1 minus f1 term is equal to 1, then f1 equal to 0, okay. So, that will be k epsilon. So, this is actually away from the wall, okay, just let me, yeah. So, this is maybe away from the wall, okay, and this is maybe close to the wall, because I plotted in 1 minus f1, okay, and you can think of it as the distance y is maybe some kind of y inverse. Okay. So, what I am saying that when minus 1 minus f1 is equal to 1, this is the behavior of k epsilon, okay, and this is the behavior of k omega. Okay. Same thing is shown here. Okay. So, when f1 is equal to 1, okay, you can see that 1 minus f1 will become 0. So, this term will go to 0, and you have the pure omega equation that you had in the standard k epsilon k omega model, and this will be your k omega model. Okay. When you go away from the wall, so your f1 equal to 0. So, 1 minus f1 is equal to 1. Okay. So, this term remains, okay, and this term actually becomes 1. Okay. So, then finally, you have a pure k epsilon behavior here. Okay. There may be typo here, the 2 may be a typo. I will basically correct it and send you in the lecture notes. Okay. In between, you have to make sure that the blending is perfect. Okay. So, you use some kind of function here, okay, so that it is not an abrupt jump from 1 to 0. It is not like at one grid point you have the k omega, another point is k epsilon, right. So, this is k omega and this is k epsilon. It will a problem, okay, because you are basically making drastic change and the drastic change is not good in any CFD simulation, whether it is a drastic change in the grid, whether it is a drastic change in the flow parameters. Okay. The solver always has difficulty if you have a very drastic change. Okay. So, in order to avoid that, we will use some kind of a blending function, and that is how you will get it. Okay. This is basically given as I think some kind of tan inverse function. Okay. So, what is the advantage of the SST omega model? So, you basically uses the best properties of the k epsilon and k omega in the respective regions. Okay, this is a very important thing, respective regions. So, let us say you use k omega away from the wall and k epsilon close to the wall, then you are just doing the worst, right, because these models are not going to work there, right. So, you are basically doing k omega near the wall and k epsilon away from the wall. Okay. Yeah. So, not tan inverse, but tan h. You use f1 equal to tan h argument 1 to the 4, where argument 1 depends on the distance from the wall. Okay. It is a function of distance from the wall. So, you take some value of the distance from the wall, take the tan hyperbolic profile, draw it, and then based on the value of this f1, the equation may be k epsilon, k omega, or may be a mixture of the k epsilon k omega. Okay. That depends on the value of f1. Okay. So, I hope you understood what is the main principle behind this SST omega model. Okay. Now, there are versions of SST omega model also. Okay. So, there is a this BST model, which is called a baseline shear transport model. Okay. Right. So, as we know in the k omega model that your nu t is equal to k by omega, right, or mu t is equal to rho k by omega. Okay. This is how you will get it from the k omega model, right. But Mentor, okay, Mentor is a is a famous modeler. You will see many models from him. Okay, you may go back and read literature about the models that he has proposed, and they are very successful models. Okay, so he proposed later that we need to introduce some kind of viscosity limiter. Okay, so you can see here there is a value called A1. Okay, and then there is another function called SF2. Okay. So, what it says that in certain regions you can get the value of k by omega, okay, but in some flows that eddy viscosity that you are getting from the k by omega is very high. It is so high that it is basically, let us say if you have a expansion fan in some region, okay, and you expect that your viscosity should eddy viscosity should go down. Okay. But this model, if you use the baseline turbulence model, it is still going to produce very high level of k by omega. So, what Mentor's SST does is basically it uses some kind of limiter here. Okay, you can see the function, this is a max function. Okay, so it will take a max of this, and because this is in denominator, your value of this k by omega, or basically effective k by omega, will go down. So, this Mentor's SST is the most popular model now. With the viscosity limiter, you can actually change this value of limiter. I think the default value of limiter is A1 equal to 0.31. You see that wherever this A1 omega is greater term, okay, you will get back to this value mu equal to rho k by omega. But when this SF2 is greater than this A1 omega, this term SS is the structure parameter and F2 is another function. Okay, so, you will have this term dominating, which is A1 rho k by SF2. Okay. So, because the denominator becomes higher, it is lesser than k by omega. Okay, that is the idea. Okay. We want to reduce the eddy viscosity in certain regions. So, this model basically gives better prediction for separated flows. In fact, this is the one of the best model for the flow with operations. Okay, so, this is very popular in your turbo machinery flows, or wherever flows you have got high curvature, or you want to you are expecting separation. In those flows you would like to use this Mentor SST model. Okay, so, I think we will stop here. In the next class we are going to discuss the transitional model. Okay, and then we will briefly look at some of the advanced turbulence models, and then we will stop the discussion about the Renz modeling. Thank you very much.